we have the final project left, and so the structure of the final project is it's going to be your final exam, and you'll be asked to model a scenario, which will require you to go out and observe some stuff. Now, when you do that, don't be weird and all go to the same place, because I'm sure if you go to a store and everyone's sitting there watching, you know, go to Target and you all stand there and watch the registers, they're gonna kind of think something weird's going on. So don't be weird about it. Um, but you're going to be asked to do a modeling scenario where you're going to go out and observe and collect a little bit of data and then choose a bunch of distributions with more than one moving part and produce a model and then make a recommendation based on samples from that multi-part model. And so we'll go over on Thursday details of the project. And the project is worth a substantial amount of the grade, and during the scheduled final exam period, which I have no control over, we will have presentations about what you are doing or have done as your project, and then that project will be handed in on the last day of finals, right at the same time you're supposed to exit or vacate the dormitories. All right. Um, so, and again, there we go. Let's see if that works. There we go. So the last bit of the reading, please, this is from last time. Make sure you've gotten caught up, and this will carry you through central limit theorem, which is what we'll end with early on Thursday and spend the balance of Thursday talking about the project. Okay, so last day of classes, some important dates. I think I posted this on the Slack channel. It's all a blur. I think I did. Yes, I did. Did it for this and my other class. So last day of classes is the 5th, which is this Thursday. So, whether it's good news or bad news, you don't have to listen to me talk about this stuff ever again past Thursday. But nonetheless, last class is Thursday, the 5th. Reading day is the day after that, Friday. On reading day, we have Pmax Day, the day formerly known as CIS Day. And so Pmax Day for the Division of Physics, Engineering, Math, and Computer Science. And that's where we get all the capstones, some master's projects, and some other class projects and things like that in a room. It's an all-day affair. It's either 8:30 or 9 o'clock. Runs through like 1 or 2 in the afternoon, and you get to hear and see all these various projects and research work being done by various individuals in the department. And so capstone is a requirement for your graduation. So it's also a wonderful opportunity to to uh, to see what a capstone project looks like. And I do make a shameless plug. Um, uh, a grad student in another department had approached me about a project idea, and I said, "Hey, that's a great idea. Maybe we could get an undergrad to do a capstone project." And this thing called the Open Knit project, and the idea is to build an automated knitting machine for which there is a DIY set of instructions. But the particular thing of interest for this project is to take that, and it's our Arduino or Raspberry Pi control, is to take the basic project and design a layout system for patterns that will then actuate or control the automated knit machine to actually weave the pattern. So the idea is to develop a system for specifying patterns and then working out the controls for the automated knitting machine that'll produce that pattern rather than the manual method. So if anyone's interested, um, you know, you don't have to worry about buying parts. That's something we handle for the department. But it'd be a great capstone project if you're interested in embedded systems, in Internet of Things, in software engineering as well. And the mechanical part is already specified. It would involve some mechanical stuff, which is a lot of fun because you can sort of, have this artifact after the fact. And who also wouldn't love, a scarf where you can specify the pattern, let the machine go for half hour, 45 minutes, and you have something knitted with the pattern. Question? Yes. Pardon? That's a great question. The practice is, well, if the capstone advisor wants it, I get to keep. No, yeah, we usually let the students keep it afterwards. We usually let the students, you know, what your student fees go towards, right, over the years that you're here. Um, all sorts of things, and know that your student fees, 100% of it is spent on you, the students, right? We get no benefit from it outside of the joy of seeing you succeed, right? But the student fees go towards that, and so if a student wants to keep it, generally it's theirs to keep. Yes, that'd be for next semester for spring. So if you're interested, or there are, I typically don't do group capstones, but for this, it's conceivable to do it as a group. And so the focus is more. I mean, there will be some mechanical part, but the focus is more on the development of a pattern specification and layout system, and how to translate that specification to actual action on the machine to re-implement the pattern. Let's continue. So there's the important stuff. Um, Please do attend reading day, Pmax day. You'll see the schedule from Rasomni. Everything is kind of late because we've all had to absorb extra work for the faculty member that departed abruptly at the end of the summer. And so things are a little bit harried this semester. So please do attend on reading day. Um, it would be in your interest, especially, excuse me, especially if you're in the market for a capstone project. Minimally, you'll see what a capstone looks like and get a chance to interact and ask those folks questions. I have two capstone students. Han is doing, well, I won't give it away. Han and Constance, some very fantastic capstones projects. So you can ask them about what they do, and you can ask them the truth about, I'm not saying you should choose me or choose someone else. Choose whichever faculty matches your style or area of interest, if their expertise matches that. But you can also ask them for the brutally honest truth of what it's like working on a capstone with XYZ faculty member. I fully expect you to do that. Okay. All right. So schedule exam. During the scheduled final exam period, I have no control over this. It's selected by administrator. I didn't pick this date. I wouldn't have picked this date, but nonetheless, for this class, the scheduled exam period is Tuesday, the 10th of December, from 10:30 p.m. to 12:30 p.m. And so the format I usually have will be the period where each of you will give a presentation about your project, right? What you are going to be doing or what you are doing, or if you're currently doing it, how it's going. And then when the residence halls close at 8 p.m. on Friday the 13th, oh yeah, Friday the 13th, on Friday the 13th, that's a very interesting choice. I just noticed that. But anyway, so on Friday the 13th at 8 p.m., residence halls close, and that's going to be the deadline for handing in your project. Now, recognize the fact that your project could be quite large, and you'll find out rather quickly that Blackboard does not accept large file attachments when you submit. And so please, for this hand-in submission of the project, please use some sort of cloud-backed storage to hand it in. If it's a zip file or what have you, or tar file, yeah, no, zip file. Um, put it on a Google Drive or a OneDrive from Microsoft product or Dropbox and just send me the link. That's fine. I'll just download it once the due date comes. And please note in your calendar, on your refrigerator, in your smartphone, that it's 8 p.m. and not 11:59, 59 seconds. In the heat of the moment, all these finals and stuff that you're going to be having coming up next week, it's easy to think that it's the usual hand-in. Don't get caught with the earlier due time from what is usual. Okay, so 8 p.m. on Friday the 13th of December is when this is due electronically. So the scheduled exam period is just for your presentation, and then the due date is when you hand in all the materials, including the slides and everything. Okay? All right, any questions about this? All right, so hopefully it'll be fun as this stuff can be, and you'll find it's actually quite interesting. And I hope many of you, all of you, some of you, will consider a career in modeling. Modeling is much easier than software because software, the language changes every 5 to 10 years. Math is the same for generations. You learn it once and you know it like an old familiar friend. Um, and so certainly there's lots and lots of work in modeling. The types of stuff that we'll be doing on the project. All sorts of people use it from the post office to FedEx, and I don't mean the retail, I mean the corporate offices, right? For all sorts of things when they design processes for restaurants and all sorts of stuff. So hopefully you'll have fun with it, and I look forward to seeing what you'll come up with because I give you leeway on the choice. And we'll talk about the project in detail on Thursday. Okay, so any questions? So please write down the date. I posted it on the Slack because every single semester there's one person, don't be that one, where they say, oops, oh, I thought it was 11:59, 59 seconds. Remember, it's 8 p.m. Okay, question? On Thursday, yes. Yes. I will certainly post it before that, probably Wednesday, since I don't teach on Wednesday. And then I will discuss the project on Thursday. Okay. Or the Tuesday. During the scheduled final exam period, that's when you'll do a presentation on it. But then the final project itself, all those materials are due on Friday the 13th. Okay. Any other questions? Make sense? No? No questions? All right. So why don't we begin? All right. So where we left off last time, we were talking about the law of total probability for the normal distribution. I'm used to calling it the Gaussian. It's the same thing. They're synonyms. We talked about law of total probability for the normal distribution, and we're going to now go to the mean and the variance. And so there's a density function for the normal distribution, 1 upon radical 2 pi sigma squared, e to the minus 1/2 sigma squared in the denominator, with x minus mu quantity squared in the numerator for that exponent. And so for expectation, it's the weighted probabilistic sum. So we have e of x is just the value x times the density function f of x dx. And of course, there's our f of x. And we're going to prove or demonstrate that when you take this over all possible values of x, x is real valued, that you get the quantity mu. Okay, so we start out and we'll just set up the problem by the definition of expectation. So we substitute for f of x the density function. So we have x times 1 upon our constant here, and I'll just call it our constant so I don't have to keep saying it, e to the minus 1 over 2 sigma squared, and we have our x minus mu quantity squared dx. Okay, so we look at this expression and we notice that our constant here does not involve our x, so it is not captured under this integral. So we can bring it out from under the integration out front, and we have our constant leading out here, and then we have our integral from minus infinity to plus infinity of x times e to the minus 1 upon 2 sigma squared denominator, and x minus mu quantity squared numerator dx. Okay, so now we take this expression and we're going to do a u substitution and use our Jacobian. And conveniently, when we do this u substitution, we're going to call it y, and we want to do it so that we have e to some single power instead of x minus mu, and then we're going to work with this and go forward. So we say let y equal x minus mu, and of course, we take the derivative with respect to x of both sides because we're going to do the substitution. What you're concerned about is the rate of change associated with that substitution, and we get dy is equal to dx. Okay, we do a little bit of manipulation, and we know what x is. We also know what dy is, and we have our original substitution. So we do that, and we make our substitution, and here we have a value x, so we're going to make that substitution x equals y plus mu, given our let y equals x minus mu, so a little bit of algebra to get to that. And then we're also going to substitute for this x minus mu quantity squared, we're going to substitute y for our x minus mu. So we're going to get a y squared for the exponent for our e to x. All right, so we do that, and we have our y plus mu here, in our parenthesized expression, and we multiply that by e to the minus y squared over 2 sigma squared, and now it's dy. Now, of course, for this Jacobian, we had, based on our substitution, dy equals dx, so we don't have any constant factor. It's just a one-to-one relationship. Okay. So now, first, any questions about this? So these are just substitutions at this juncture, and we're factoring out this constant because it does not involve x anywhere. All right. So now we have this expression, and we have this e term multiplied by 2 terms in this parenthesized expression, and so you certainly have the law of distributive property of multiplication over addition. And so what we're going to look at is each term as a result of this multiplication. And so we have our leading coefficient, integral, and we have y times this e to the exponent, and we have plus mu times e to the exponent, and we're going to consider each term as a result of that multiplication. We're going to consider each term one at a time. Okay. So the first thing we do is we'll look at this constant here, leading constant, times the mu term in this parenthesized expression times this e, because this e term multiplies both of those terms in that parenthesized summation. And we can certainly look at each of those terms separately. So let's look at our first term. So we have 1 over radical 2 pi sigma squared times mu times e to the minus y squared over 2 sigma squared dy, right? So we're basically evaluating this integral for the first term and then evaluating this integral again for the second term, adding those two results together to get our answer. Okay. Does that make sense? Any questions? Okay. So let's continue. So for that, if we do this integral, well, what we end up with, we have radical, this constant, and we have the integral from minus to plus infinity of mu, and then we have our e term. So if we were to kind of think about this longhand, did I bring a marker? No, I did not. Maybe have it there. Hope this works. So if you think about it, we have integral from minus plus to plus infinity of 1 over radical 2 pi sigma squared mu e to the minus y squared over 2 sigma squared dy. That's our first term. And when we do that integral, well, we can do a substitution here, a u substitution. And when we do that u substitution, we end up with an expression and we compute the definite integral from the indefinite integral. And if we do that definite integral from the indefinite integral, this plus and minus infinity, you'll notice this exponent is squared. So it doesn't matter if we have plus infinity substituted for y or minus infinity, it's always going to be e to the minus y squared, some power, right? If you substitute y is infinite. And e to a very large exponent is just e to a very large negative exponent is just brain fart. I am so tired right now. Things cancel out. You can do the math yourself. Things cancel out, and you end up with the expression as 1. You can, don't believe me, try it out yourself. So actually do the substitution, express the definite integral from the indefinite integral, you evaluate it, and all of that madness with the e to some exponent goes to 1 when you do that definite integral. So it's the evaluation of the indefinite integral at plus infinity minus the value of that indefinite integral evaluated for y equals minus infinity, and it all goes to 1. It all cancels out. And so you're left with this mu times something that's, actually, no, don't do it that way. I'm thinking of something else. All right, so let me see. We'll do it more easily. Yeah. Okay, all right. So we... Okay. All right, so we take this mu. Let me do it a different way. Let's see. Well, oh, yeah. Total probability. Okay. So we take our expression. Let me start over. Rewind. I'm going to cut that part out of the tape. We have our expression here. Our mu does not involve y. And here, when we did the change of variable using our Jacobian, our substitution, let y equals x minus mu, we have a dy here. And so everything involving a function of y is captured under this integration. And so because of that, if we look at this mu is a constant, right? It does not involve y, so we can factor that constant out. So we started out with an expression from minus infinity to plus infinity. We had 1 over radical 2 pi sigma squared. Now I'm remembering. Mu e to the minus y squared over 2 sigma squared dy. Now this mu does not involve y, so we can factor that out. So we have mu integral minus infinity to plus infinity, 1 over radical 2 pi sigma squared e to the minus y squared over 2 sigma squared. Okay, dy. So this looks exactly like the density function for a normal distribution, only instead of saying x, we're saying y. And if you look at this y squared, That's like saying y minus 0 quantity squared. So that almost looks like a density where this mu term is equal to 0. Now, as a density, of course, we just got done saying when we did the expression or the proof for law of total probability, this expression, integral from minus infinity to plus infinity of the density of a normal distribution centered at 0, mu is equal to 0, that's equal to 1, right, by law of total probability. So we can take this expression, that integral, and replace it with 1. I mean, you get the same result if you actually did the integration by parts, but why do it the long way when you can do it the easy way, right? And so if that goes to 1, we're left with mu times 1, which is just mu. And that's what I was thinking of. All right. So don't get 4.5 hours sleep before you're going to go teach. All right. So that first term involving that mu term in that parenthesized expression, if we were to evaluate the integral, we have the leading coefficient times mu times e to the exponent dy. That portion of the integral is equal to 1. Okay. Does that make sense? I apologize for that brain fart. It happens sometimes. All right. So now we'll look at the other part of the expression. We'll look at this y portion. Now this y portion, it is a function of y. It's y to the 1 power, and it is captured under the integral because our integral is with respect to dy. So we cannot do any factoring like that. And so what we have is this integral minus infinity to plus infinity, 1 over radical 2 pi sigma squared, y times e to the minus y squared over 2 sigma squared dy. Okay, so we're going to evaluate this expression. And so this expression looks like the following, right? We're going to do that integral. And so we can pull out that constant 1 over radical 2 pi sigma squared. It's out front, pulling it outside of the integral because it does not involve y. So it's not captured under the integration. And so when we look at this integral, we want to reduce it, and we're going to make a few observations about it first. Now, this is a so-called odd function. And this odd function, we're going to look at the structure of the function and use the structure of the function to help us in the simplification of this integral. Okay, so this is what an odd function looks like. An odd function takes on negative values when the domain is negative. So if you have y equals negative, right, value, it's going to be a negative, right? And you'll see here this curve is below the y equals 0 line, right? It's still symmetric, but one half of it is negative and the other half is positive, and that's the definition of a so-called odd function. And so the reason why this is important and why I point this out is because if it's an odd function, we can compute the area under the curve between minus infinity and plus infinity by just looking at half of it. Because we know for that portion that's from 0 to positive infinity, we just negate that area and add it to that area of the part that's greater than 0, right? So you only need to do it for half of it piecewise, as it were. So we're going to take a look at this. It's symmetric about origin. So here, if we have some area A for the part that's greater than 0 to infinity, we take that same area and we just negate it, add the two together, okay? And just so happens area plus negative same area is going to equal 0. Okay. Any questions about this? Does that make sense? Yeah? Okay. So let's take a look. So we take this interval from minus infinity to plus infinity, and we split it up piecewise, that half of it from minus infinity to 0. So we have minus infinity to 0 in our integral, y e to the exponent dy. And then we have the positive part, integral from 0 to positive infinity, y e to the exponent dy. So we're just going to focus on one part of it, and we're going to do a substitution here. And for this substitution, we're going to say let u equal y squared upon 2 sigma squared, because we want e to some exponent, not e to some complex exponent, because that's going to simplify the calculation of our integral. Okay, so if we do that u substitution, we need the rate of change associated with that substitution. So we take d dy, this expression. We have du is equal to y upon sigma squared dy. We do a little bit of algebra, and we say if we're going to switch from y dy to du, we have a constant factor change of sigma squared. Okay, so we're going to use this substitution, and we're going to do the integral here. Now you'll notice for this integral, I have a y dy, okay, y dy, And whenever I switch from dy to du, I need a factor of sigma squared, right? So I'm just going to use that fact from my u substitution. Okay, so I'll make that substitution in place. So here, this is the left half, the negative half for the first term, and this is the positive half for the second term, right? And I'll just show you here, I have y dy, e to the exponent, and now it becomes sigma squared e to the, that should be u squared du. Okay, that should be u squared du. Another typo. All right, so I make that substitution, and oh yeah, all right, I do that. Okay. I first substitute my y dy, right? And then I do the u part, my substitution, and I'm left with e to the minus u instead of e to that complex exponent. Does that make sense? Any questions? So I start out with the u substitution. I compute the Jacobian, the rate of change, and then I first substitute the y dy with that rate of change sigma squared du, and then I substitute for that e to that y squared over 2 sigma squared. I substitute u for that expression. Okay, so now I have the negative component, integral from minus infinity to 0 of sigma squared e to the minus u du, and then I have the positive part, integral from 0 to infinity, sigma squared e to the minus u du. Okay, so now, of course, the integral, let me just take into consideration the positive part, because I know this is symmetric. Whatever I get for the area under the curve, the integral for the positive part, I negate that and add it to the result for the positive part, and that's the area for the entire thing from minus infinity to plus infinity. So I take this positive part and I look at that integral. It's just a straightforward integral. It's minus sigma squared e to the minus u, and I evaluate that indefinite integral at the endpoints to compute the definite integral. So I evaluate that for u equals infinity and u equals 0. So for u equals infinity, of course, that's negative infinity, so that goes to 0. And then I subtract from that the evaluation of this expression for u equals 0, which is just minus a minus sigma squared. So minus and minus sigma squared are just sigma squared, right? So there's my result for the integral of the positive component. So I just add the negative of this, negative sigma squared, plus the positive of this, sigma squared. That's minus sigma squared plus sigma squared is equal to 0. Now, of course, knowing that it's an even function, already knew that, but we still have to demonstrate that rigorously mathematically. Okay. Any questions about this? Does that make sense? All right. So it's a straightforward integration. And so we get the integral between minus infinity and plus infinity of our original expression for this odd function is 0, okay, based on that symmetry property. All right, so going back to what we had, the first component we said for this integration, we said that it looks like the normal law of total probability, and we got mu times 1, which is mu. And the second component, we just showed it's an odd function, and its integral is 0, right? So this integral portion, minus infinity to plus infinity of y e to the minus y squared upon 2 sigma squared dy is equal to 0. So for that second term, we get 0. And so mu times 1 plus 0 is nothing but mu. And we've demonstrated now that the expectation of a normal random variable is just mu. Okay. Any questions about this? Does that make sense? All right. So let's go to the variance. And the variance of a normal distribution, a normal random variable, is as follows. It's sigma squared, but we're going to demonstrate that. So what is variance? Variance is just the probabilistic sum or probabilistic average of the difference between each measurement and its mean, and you care about the magnitude but not the direction, so you square that difference. So we have x minus mu quantity squared times our density function. There's our density function up there to the right, 1 upon radical 2 pi sigma e to our exponent x minus mu quantity squared negated over 2 sigma squared. And so we plug in for what the density function is, and we get this expression. And so now we're going to take our substitution. We want to get rid of this complex exponent, so we're going to also get rid of this leading term here. We're going to let y equal x minus mu. So we're going to end up with a y squared here, and we're going to end up with a y squared in the exponent, and then we're going to use integration by parts to reduce it. But when we do the integration by parts, we're going to tease apart the f function and the g prime function a little bit differently to make things work out a little cleaner. Okay, so there's our substitution. We look at the rate of change associated with that substitution, and it's a one-for-one substitution. So everywhere we see a dx, when we go to y, we're just going to substitute dy. So that doesn't change, but our definition based on the substitution of x is just y plus mu. So everywhere we see x, we could, if we needed to, just substitute that with a y plus mu. Okay, so we make this substitution. So this x minus mu now becomes y squared, because y equals x minus mu. And this x minus mu in the numerator of the exponent part for e becomes y squared. So we have this y squared. There's our leading coefficient with our radical. We have e to the minus y squared upon 2 sigma squared dy now. Now it's dy because our substitution does not have a constant factor. It's just a one-for-one substitution when we go from dx to dy. Okay. Any questions about this? Does that make sense? Yeah. All right. So now we're going to do our integration by parts. And we note that this leading coefficient does not involve y, so we can factor it out of this integration. It's not captured by dy. It does not involve y, so we can move it out, factor it out. And we have this integration here. And we're going to use integration by parts, but when we do so, we're going to select our f of x function and our g prime of x function a little bit differently. Now you could select your f of x function equals y squared, but that would require you to unwind this integration by parts 2 times, right? But you can do this a little bit simply, knowing that this is a squared term. You call this function a little bit differently when you associate them into 2 functions, f of y and g of y. Okay, g prime of y. So what we're going to do is we're going to call, where was it? E to the minus y dy. That was y squared. We had our leading 1 over radical 2 pi sigma squared. So here, our y squared is nothing more than y times y, right? And so when we associate these this expression into 2 functions, we're going to call the first y our f of y. So f of y is just equal to y. And then this other part, y e to the minus y squared over 2 sigma squared, we're going to call this our g prime of y, okay? And so, of course, if you have f of y times g prime of y, you get back the original expression. And so when you designate an expression in a complex integral that you want to simplify using integration by parts, you can split that expression up into 2 functions, f of y and g prime of y, any way you want to, right? If you make the right choice, when you simplify, it'll get easier. If you make the wrong choice, it'll be more complicated. Now, absolutely, I could have said f of y is equal to y squared. And if I did that, well, the first time you did the integration by parts, in computing your f prime of y, you're going to get 2y, and then you have to do it again to simplify further. So you can do this in one step by just choosing your f of y term and your g prime of y term appropriately. So in this case, if f of y is equal to y, that means we only have to, excuse me, apply this integration by parts once in order to get the simplification. All right, any questions about this? Does that make sense? Yeah. All right, so let's do that. So if our f of y is just y, our f prime of y is 1, okay? That's a simplification. And if our g prime of y is y times e to the minus y squared over 2 sigma squared, then our g of y, which is just the integral of g prime of y, is minus sigma squared e to the minus y squared over 2 sigma squared. And of course, the reason for that is that when you compute g of y by taking the integral of your g prime of y dy, you're going to do a u substitution, and you're going to get a cancellation of that leading y term in the original expression. Okay? So that's why that y was associated with the e term when you designated the g prime of y function for your integration by parts. Okay, so now when you do your integration by parts, you're going to say f of y times g of y minus the integral of f prime of y g g of y dy. Okay, all right, so let's do that. So when we do that integration by parts, right, we will specify that f of y, g of y, so f of y is just y, g of y is minus sigma squared e to the minus y squared over 2 sigma squared, right? That's where the first term comes from. And then we say minus the integral of f prime of y, which is just 1, times g of y dy, which is just minus sigma squared e to the minus y squared over 2 sigma squared dy. Okay? And that's where that second term comes from. So if we say minus some integral of something that has a minus, that's the same as saying plus 1 times our sigma squared e to the minus y squared over 2 sigma squared dy. Okay? So we take this expression, and this expression is just a u substitution and an integral. A u substitution and computing our integral, we take the Jacobian based on the u substitution, and we get the following expression, right? But before we reduce that, we can take this first term that we arrived upon by multiplying the f of y times the g of y. That's part of our indefinite integral. We're going to evaluate that at the bounds of integration. So we evaluate this at positive infinity and at negative infinity. We take the evaluation of this first term at positive infinity, and we subtract from that the evaluation of that term at negative infinity. And one of the observations we make, we're substituting for y. Now here we have a y, but for the exponent of e, excuse me, voice is running out. For the exponent of e, we have a y squared. So regardless of whether this is positive infinity or negative infinity, this is still going to be e to the minus something really, really big. Now, e to minus something really, really big in terms of the exponent is just 0, right? And that e to the minus y something is exponentially increasing. That y, it's also infinity. It could be minus infinity or plus infinity, depending on what infinity is. But this is going to go to 0, right? Because e to the minus power is like saying 1 over e to that power, and y is always a squared term. So this term is always going to be 0. It's going to say minus 0 minus a negative 0, right? So that's always going to be 0, that first term. And so we can just write 0 for that first term, right? So what remains then is to compute this indefinite integral for that second term. We have a leading coefficient sigma squared. We have that other constant that we factored out, 1 over radical 2 pi sigma squared. And we just need to evaluate this integral. So if we do that, one of the things we observe is if we take that integral, we have integral from minus infinity to plus infinity. We have that constant 1 over radical 2 pi sigma squared. And we have a leading sigma squared. That's a constant. It's not captured underneath the integration because that integration is with respect to dy, and that sigma squared does not involve a y anywhere. And we have our constant, and we have e to the minus y squared over 2 sigma squared dy. Now, if we look at this expression, that y squared in the numerator for e's exponent looks a lot like saying y minus 0 quantity squared, right? That's the same as y squared. And that looks a lot like a normal distribution, and it is in fact a normal distribution, assuming that the mean mu is equal to 0. And so going by law of total probability, well, this is like saying, let me take the area under the normal curve for the normal distribution for all values between minus and plus infinity, and this goes to 1, right? By definition of the law of total probability. So we're left with sigma squared times 1. So we have our sigma squared. All of this goes to 1. Our first term was 0, and we add to that sigma squared times 1, which is just sigma squared, and we're left with sigma squared, which is exactly what we were had set out to prove. Okay. Any questions about this? So it's a substitution it's making use of the law of total probability, and then it's a little bit of algebra. And we have shown now that the mean of the normal distribution, sometimes it's called the Gaussian, is mu, and the variance is sigma squared. Okay, no questions? Any questions? Okay, so why don't we continue on in the time that remains, and I'll only introduce the standard normal, and then we will, well, I might be able to just finish the whole thing. We will finish the balance of the next module on Thursday and spend the majority of Thursday talking about the final project. Okay, so let me switch off here. Don't save. Is this? Okay, yeah, that's the right one. All right, so why don't we start the next one? So now we've talked about the normal distribution, and now we're going to kind of motivate this idea of what it means to standardize a normal distribution. But before we do that, we need to talk about standard normal, and then we'll end today with talking about why you have a standard normal distribution. So again, I just spoken before. These are key dates. Please, I posted them to the Slack channel, but please be aware specifically about the final exam period where you do your presentations, as well as when the due date is. It is 8 p.m., not 11:59 and 59 seconds on Friday the 13th. So we talked about the normal distribution, and we just, last time we showed the law of total probability, and we just now got done with showing the expectation is mu and the variance is sigma squared. So let's segue to the so-called standard normal distribution. It is a normal distribution. Now, what does it mean to standardize? Now here we have a typical normal distribution. This is the classic bell curve shape. And we said that normal distribution well defines values that are so-called inertial. They're real valued, so it's a density function. But these real values, things like temperature, pressure, distance, position, velocity, are inertial, meaning that the future value, if these things change in time, is always the current value plus or minus some small amount, right? It never just jumps some dramatic amount without going those values in between. So this is our normal distribution. When you think about what these parameters mean, the things that define the normal distribution are mu, the mean, sometimes called the location, and sigma squared, which is the variance, which is sometimes called the scale. Now the variance, if you take the square root of it, that's called the standard deviation. And that standard deviation is a description of how spread out the probability mass is above and below the mean. So you can think of, to the left of the mean, smaller than it, as being below the mean, and to the right of the mean, larger than it, as being above the mean. And so the more dispersed, or the more values that you see, right, when you're observing a system that's governed by a normal distribution, the more dispersed they are. So let's say, you're talking about share prices for a stock. Let's say that share price, it started out at the opening of the trading window at, say, $65 a share. And one company's stock, it fluctuated up and down, but for the day, it went up as much as $5 to 70, or as low as $5 less, down to 60. Let's say you have another security, and let's say it also started at the opening of the trading window at 65, but it went as high as 75 and went as low as 55. So the first one, it varies less. So its standard deviation, its swing, was only plus and minus $5. The second one, its swing in price was only plus and minus $10, so its standard deviation, sigma, was more. Now, the reason why people care about this, at least in the financial markets, they call this variability, they call it risk. Because if you think about it, if you buy a stock and all of a sudden it varies a lot more, it swings more wildly above and below the mean, that means, all things being equal, if you decided to just sell it at some point, if it swings a lot, well, you could lose a lot more money, right? But on the flip side, if you know what you're doing, you could actually gain a lot more money. You wait until it swings low, you buy. You wait until it swings high, and you sell, right? Buy low, sell high. Okay, well, that's all well and good. But what happens if you have two different systems? And let's say those two different systems, you want to compare the variability. We can easily compare variability between two items that traffic, or two systems that traffic in the same quantity, share price. But let's say, if you have customers arriving in a store, and then you also have the, velocity of a car, right? How do you compare those variabilities? Which one is more variable? It's kind of hard to think about that. One is a normal distribution, one is a Poisson. What happens if you're talking about the expected number, the number of customers you interview, people you interview before you hire? How do you compare that variability to the number of people that come into a store? That's a Poisson. So one is geometric, one's Poisson. What about algorithmic execution time, right? You have some process, and let's say that process is not just a web server. Let's say you go into Subway. It takes a certain amount of time to get the bread, a certain amount of time to put the meat or vegetable items, the protein, whatever, on the bread. It takes a certain amount of time to toast it. They get toasted or not toasted. It takes a certain amount of time to apply, the condiments and the vegetables and all that other stuff. So each amount takes time. So you could certainly look at the amount of time for that multi-stage execution, describing the time when a customer orders a sandwich to the time when he or she gets that sandwich at the point of sale system and pays for it, right? So how do you compare variabilities if it's not the same quantity in which they traffic? Well, that's where the standard normal comes in, but we need to first talk about the normal distribution. So this normal distribution has parameters called location, and that's what the mean does. If you think about it, the center of this distribution describes its location, that's the mean, and you can move that location. So I can take this mu, and if I made mu smaller, the whole thing, it's like I picked it up and moved it to the left. If I made it larger, it's like I picked this whole thing up and moved it to the right. It's still the same amount of variability. It's just the center of it, its mean, its average has changed, right? So if a stock sits at 65 average and it goes plus or minus 5, that's the same type of variability as a stock being 100 going plus or minus 5. They behave the same in terms of the variability, even though their center is different, okay? Any questions about this? Does that make sense? And so this type of distribution has what's called a location scale parameterization. And you define a distribution, its behavior, in this case by its location, what the center value is, and by its scale, which is this dispersion as measured by the standard deviation, the square of which is the variance. Okay. Now other distributions like the Poisson has a shape parameter. As you change the lambda for the Poisson, it becomes more skewed and it kind of mushes to the other direction as you change lambda, right? So this is a so-called location scale model, normal distribution. All right, so when you change mu, what happens? So here we have some value of mu. Let's say mu is 5, it was 10, or in the case of stock it's 65. If I change mu to 0, I can do that by taking all my data points that I observe. I take the mean, compute the mean, and then I take each data point and now subtract from it the value of mu. If I do that, watch what happens. I basically take origin, this 0 point, and I move it to the center, right? And so this idea of centering a distribution says I want to change the value of the data points so that the center of the new distribution, the transformed data, is now 0, right? And that's called centering your distribution about origin, right? Origin is 0, and centering about origin meaning you want to do something to each data point so that when you recalculate the distribution, something in MATLAB, you take the histogram, you'd see that the center of mass, i.e. the mean, mu, is now 0, okay? Right, any questions about this? Does that make sense? Okay, so now one of the things I can do, okay, if I centered my distribution, that makes it easier to compare the variability. If I had two stocks, one had an average of 100 and it went up and down plus and minus 5. The other had an average of 65 during the trading day and it went up plus and minus 5. I could absolutely compare the two and say, yep, they both have the same type of dispersion, the type of same scale. They both vary plus and minus the same amount. If I center it about origin, you can make that apples to apples comparison, so to speak. Now, but there's a problem here. The problem has to do with this scale. Because if you notice, if I said I had $20 and after I'm done, I had 30, what was the percentage increase? You'd say it increased by 50%. If I said I had $100 and I ended up with 150, and I said, what's the percentage increase? You'd say, yeah, that was also 50%. Now, the problem is when you talk about dispersion and you talk about percentages, that word percent, per centum, centum is the Latin for 100 per 100, it's a standardized way of comparing things that allow you to talk about the relative change in terms of dispersion, right? And so now we need a way to, similar to how we centered the two, those distributions by subtracting zero from the mean from each data point, it centers it about origin. We need to do something with the scale parameter. And how we do that, well, if we have the scale and, excuse me, the dispersion goes up and down some quantity or amount we call sigma, the square of which is sigma squared, the variance, then if we took our data and we divided by sigma, that's going to kind of shrink everything down to something that looks like a percentage scale. And now we can make a fair comparison between things that both increase by, say, 50%, but one of them, an increase of $50 is 50%, but the other, an increase of $10 is also 50%. You need to be able to make dispersion comparisons on the same scale. So now we've centered our distribution, our normal, about origin. And what happens when we change sigma? Well, if we multiply by 1 over sigma, that's the same as dividing by sigma. You take each data point and you divide it, once you've centered it, by sigma. Now what you're doing is you're taking this distribution, now that it's centered, and watch what happens to our sigma. Well, it's now a sigma of 1. So we started out with some sigma that might be plus or minus 50, might be plus or minus 10, right? Because it's both the same amount of dispersion. But now it's plus or minus 1, right? So we have two things that happened here. We centered about origin by subtracting the mean from each data point. And then we divided by the standard deviation, right, after we centered it. And that shrinks everything down proportionally down to something that looks like a percentage scale. Now we can make fair comparison between things. They might change the same amount, but the percentage by which they change is the same, but the actual hard value by which they change is different. So now we can say, okay, if we have a stock that increases by 50%, one could be average of 100, and it can go up to 150 or down to 50, and the other could be $20, and it can go up to 30 or down to 10. And now we can say, aha, they look exactly the same, and the proportion by which they change is the same. So yes, they do behave similarly. Does that make sense? So this process of centering about origin and dividing by standard deviation is called normalization. And the whole purpose of normalization is so that you can make a fair comparison between two distributions of the same kind, right? Now, I stress at this point at the same kind because what we'll talk about when we talk about central limit theorem is a tool that says now they can be different kinds. You can have a geometric and a Poisson. You can have a gamma and you can have a binomial. And now you can transform them to an equivalent normal distribution and then normalize them. And now you can make comparisons between things that originally were very different from one another. Does that make sense? Any questions? Okay. So let's take a look. So what does this look like? So we have a variable x. It's a random variable. It takes on a value little x, and x is distributed as, that's what this tilde, how it's pronounced. It's distributed as a normal distribution, and that normal distribution has a mean of mu, and it has a variance of sigma squared. And if it has a variance of sigma squared, its standard deviation is sigma, the square root of the variance. Okay, you can transform this to an equivalent normal distribution where the mean is 0 and the variance is 1. And if the variance is 1, take the square root of that, and the standard deviation is also 1 because the square root of 1 is also 1. Now, this is called transforming from a normal to what's called a standard normal. And when you express a standard normal, typically in the literature and in the book, they call it a z. Now, sometimes in the literature, you also talk about a z distribution. A z distribution is just a normal distribution that has been normalized. And you normalized by the following procedure. So let's say you have temperature, or you have pressure, or you have distance, or you have velocity. You take all your measurements. Let's say you had 100 measurements. You take each measurement and you compute the mean, and then you subtract from each measurement the mean over all of your 100 measurements. And then that result, you're going to take that result and multiply each one or divide each one by sigma, by the standard deviation. The resulting value, if you were to compute the histogram or take the distribution of it, it's going to look like this standard normal. So now it's in a standardized normal form. And a standard normal is nothing more than a normal that has been centered about origin and scaled down by the standard deviation. Okay. Any questions about this? Does that make sense? So this is a really powerful mechanism, and the reason why is that now you can do hypothesis testing. You can say, is this temperature an oddball relative to 95% of the temperatures that I observed? Yes or no? Is this email an oddball relative to 95% of the legitimate emails that come into my mailbox? Is this heart rate an oddball relative to 95% of all the heart rates that I detect? So if you want to know, let's say you have a watch platform, which is popular now, and you have continuous heart rate, and is somebody experiencing irregular heart rate, right? One of the things you do, you take a whole lot of measurements of heart rate. Heart rate is a normal distribution. It's an inertial quantity. You don't go from a heart rate of like, I don't know, 90 beats per second, all of a sudden, next instant, it's 140, right? It doesn't happen that way. It goes up incrementally. And so you take heart rate samples, compute a normal distribution, standardize it, and then when you get a new heart rate measurement, you say, is it typical of 95%? And you can do that with this standard normal, okay? If you wanted to get back to the original measurement after you've normalized it, you just do a little bit of algebra. You multiply this new value, z, times the standard deviation, and then you add mu to it, and that result gives you back the original measurement before you did the normalization, okay? Any questions about this? Does that make sense? And so this is used, it's a very simple sounding concept because it is. It's actually quite beautiful, quite elegant in its simplicity, but you can use it to do all sorts of stuff, right? So one of the things you could do is you could say, oh, is my heart rate typical? And is my EEG typical? You can have multiple measurements and now say, how does this variability of one relate to the variability of the other? And do lots of powerful things with it. Any questions about this? Does that make sense? So it gets a lot more fun when you actually get to use this stuff. We have 9 more minutes. All right. So this is the PDF of the standard normal. And of course, the standard normal, it's a density function, is nothing more than the normal, but you're substituting mu equals 0 and sigma squared equals 1, right? So it simplifies quite a bit, but it is still a proper density distribution. And of course, you have a CDF. CDF has not changed. It's the integral between minus infinity to that value x for which you want the partial area under the curve of the density function dx. So that hasn't changed. So now, why is this important? Now, if you think about what percentages did, you can compare things based on percentages even though the values are different. In similar fashion, with normalized or standard normal, you can now compare distributions that are normal regardless of the actual values. And that's a really important, powerful thing. So if you have two temperatures, temperature in one geographic location, temperature in a different geographic location, and you want to say, is the temperature of, Dover, let's say you want to start a winery, right? And I hope you do. Give us a discount. Let's say you start a winery, and you know that certain types of grapes grow well in certain regions. So you have things like temperature, pressure, humidity, and stuff like that. So you want to have an average temperature, and you want to have a similar variability in the temperature. It doesn't get too hot, it doesn't get too cold. So you might say, okay, let me check the temperature profile of various locations in the world. And let's say the Normandy region in France, you want them to grow like the grapes in Normandy, and you want to find some other place in the country that's similar to Normandy. So you want the average to be the same, and you want the variability to be the same. So now you can start to make that fair comparison using the normal distribution and standardizing. So we have the normal distribution in one location, and you standardize it. Now it goes from actual temperature values to what looks like proportions of temperature values. So you notice here, because the standard deviation is 1, now it's point something, point something, point something. And that's what a z distribution typically looks like. You have fractions, right? And It's now easier to compare two locations. If one location looked like this, it goes from 0 to 0.1 to 0.3, 0.6, and here you have 0 going to 0.1, 0.2, 0.3. Well, they're not the same, right? It's much easier to make a fair comparison instead of dealing with actual degrees Fahrenheit or degrees Celsius. Okay. Any questions about this? All right. So let's kind of motivate this last section, central limit theorem, and we'll just pick up from there. I have about 5 minutes left. And so the central limit theorem provides, when we talked about standard normal distribution, we talked about fair comparison between two things that are normal distributions. Things like heart rate, it's inertial and it's real valued. Things like EEG, it's real valued and it's inertial. Things like position, velocity, and so forth. And so they both have to be normal distributions. What happens if they're not normal distributions? What if I want to compare, the time behavior of the sandwich line at Subway with the customer arrival rate for that same Subway, right? And I want to ask, does the behavior of the sandwich line change as the behavior of the amount of customers changes over time? That might be something you'd want to know, right? It's important when you're deciding how many lines should I have, how many employees should I have. So the central limit theorem provides a tool that allows you now to say, let me take two distributions, even though they're different distributions, I can now make them both look like normals, then I normalize them to standard normals, and now I can compare them. And so the central limit theorem now allows us to cast, if you will, two different distributions as if it was a normal distribution. So let's take a look. We have some random variable, and it's distributed as some distribution. Could be Bernoulli, could be binomial. We talked about the geometric. We talked about the gamma, talked about the negative binomial. We talked about the uniform. We talked about the normal. We talked about all sorts of stuff, right? Talked about Poisson. So we have some variable, x, and it's distributed as some distribution. And it has some parameters that define it. It might be location scale. It might be just a shape parameter that kind of mushes the distribution in one direction or another. And so there are many types of operations on sample data that involves a sum, right? So let's think about that a little bit. Suppose instead of just the plain heart rate, what if you wanted to know the rate of change of the heart rate? Well, from calculus, when you talked about the derivative, you said the derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So what is that saying? Well, suppose you have a graph, and this graph is the heart rate, and time increases going to the right. And you have on the vertical axis, you have beats per minute. And let's say you start out baseline of like, say, 70 beats per minute, right? Okay, so let's say all of a sudden it starts going up, and then it sits there, and then it starts going down again, back to 70. And let's say it goes up to about 80 beats per minute. Now, of course, when you sample this in time, what are you doing? You're saying to your heart rate measurement, get me a heart rate, get me a heart rate, get me a heart rate. So here, your f of x is here, and f of x is going to change over time. Really, it's just f of t, right? Let me just call it f of t instead of f of x. Now, here it's at time t equals 1, it's 70. Maybe t equals 2, it's like 72, right? T equals 3, it's like 73, and so forth. Now, what does this say? When I say that delta x in the denominator, what I'm saying when I say limit as delta x goes to 0, I'm saying what is the smallest change in x that I can have? In this example, it's every second. If you have a device that you can use to measure heart rate 10 times a second, it would be 1/10 of a second, right? So that's what this delta x means. What this f of x plus delta x minus f of x means. Well, here's my f of x. X is equal to 1. My delta x is 1 second, so that delta x equals 1 second, or 1. And then here, my f of x plus delta x, that's the next value. So here, f of x plus delta x is equal to 72, right? That's this value at time 2. F of x at time 1 is equal to 70. So I have f of x plus delta x minus f of x, that's 72 minus 70. Delta x is 1 second. That's just 2 over 1, or a change of 2, right? So that's what that derivative means. Now, when I take this derivative, what am I doing? I'm taking 72, and I'm adding to it a negative 70. Well, here's an addition. When you compute a derivative, you're doing an addition, and then you're multiplying that by 1 over 1, right? It doesn't have to be 1 over 1, it could be 1 over 2. So here it is. I have an addition or a sum of a bunch of values, and a subtraction is nothing more than adding a negative, and I can multiply by a scalar. If I were to take, instead of the derivative, what if I said the average heart rate? Well, one thing I can do for the average heart rate is I can take a bunch of measurements. Let's say I take 10 measurements, 4, 5, dot, 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 up to 10. I take each of those measurements and I compute the mean, right? The average. So that average, if I said 1 over 10 times f of t at time 1 plus dot, 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 f of t at time 10, guess what? That average is nothing more than the sum I multiply by a scalar. So many transformations can be made on data, or statistics can be computed on data that employ a sum, right? Does that make sense? And any questions about this? So I'm trying to convince you that the sum is all over the place in a lot of calculations. And you can use this sum in order to, you can use this transformation, the sum, and when you do that, regardless of the distribution that those things you summed came from, if you sum enough components together, the result will look like a normal distribution, okay? And the central limit theorem describes that relationship, okay? So we'll stop there. It's time, and we'll pick back up with the central limit theorem and spend the balance, or first part of Thursday, talking about CLT, and then we'll finish up and then talk about the project, okay? Any questions? No? All right. So with that, we'll end there. I'll see you on Thursday.